Okay, so hello everyone. Thank you for being here today. My name is Carlos. Today we'll be talking to you about the numerical shape optimization library that I have coded during the first year of my PhD. So let's get right to it. The talk is divided into two parts. First, the introduction. I will talk about Rodin's main features that can serve in shape optimization. And in the second part, I will show a small numerical example and how you can implement it with Rodin. So first of all, what is a shape optimization problem? Let me maximize this. Can you still see my screen?
Yeah, looks good.
Okay, so what is a shape optimization problem? A shape optimization problem is just an optimization problem where the optimization variable is the shape of the structure itself. So I won't spend too much time on the actual meaning of this. I will only give some general references. Specifically, I will cite the review paper, last year's review paper by Grégoire Allaire, Charles Dapogny, and Franz Hajoub. It does a good job at explaining numerical shape optimization and what it's all about. And I'll leave you with some other general classical references. I have also selected some sample applications, which I have enjoyed reading during the first year of my PhD. So if you're interested, go check them out. So what is Rodin? As I already said, it's a numerical C++17 library, which facilitates the implementation of shape and topology optimization algorithms. So it wraps around various numerical libraries and utilities and puts them all under one single API. And of course, wrapped libraries include MFEM, MMG, if anyone's familiar with MMG, I'm sure you're not surprised, and the ISCD tool suite by the Sorbonne University. So above all, it is a tool for the rapid prototyping of shape optimization algorithms. So if you're interested, you can find Rodin by following these links after the presentation. It's hosted on GitHub and it's totally open source. So what does Rodin do? It allows for easy specification and resolution of variational problems and provides some uniform class interfaces and transparent conversions between different types of meshes. So for example, converting between an MMG mesh and an MFEM mesh. Enforces some semantic rules related to weak formulations. So for example, differentiability of trial functions and test functions. And it also adds some functionalities of its own on top of the wrapped classes. So how does Rodin do it? MFEM is used for assembling and solving the linear systems related to the weak formulations. We will see how it does this. MMG is a meshing and remeshing tool with a suite of features to operate on meshes. And well, most notably, I use it to improve the quality of my meshes. And the IECD toolsuite is a collection of tools which include advection of a level set function, distancing of a domain, etc., etc. If you're familiar with shape optimization, I'm pretty sure these concepts will be familiar to you. So first of all, I want to see how to solve a partial differential equation in Rodin. So you have your regular Poisson equation with a Dirichlet boundary condition on the boundary, gamma. And typically you derive your associated weak formulation. So this is very classical. So in Rodin, it's usually achieved within 4 lines of code. You define the problem Poisson by specifying a trial function U, trial function V, and then you just build the expression syntactically, all in native C++ code. So you write integral of the dot product of gradient U, gradient V, times lambda, minus the integral of the multiplication of f times v, plus a Dirichlet boundary condition on gamma. So I will give just quickly the full code. You can solve a Poisson equation in 24 lines of code. So you include Rodin's modules using the namespaces. You load the mesh using this API. You define your parameters. You build a finite element space, an H1 finite element space. You define your trial function, your test function. As previously shown, you construct the Poisson problem, and then you just solve the problem using a CG solver. All of this functionality is provided usually by MFEM. It's just a wrapper. And you just save your solution. So to show you the quick result, you just visualize it by GLBIS, MFEM's companion tool. And this is the result, I think you can find this in the example page of MFEM. So this was the weak formulation specification. So what is the integration with MMG? So the integration with MMG is that it natively supports the MEDIT file format, usually used by INRIA, if you're familiar. And it also supports all the tool suite of MMG, so namely mesh optimization and others. I won't put the whole list here because there are too many, but you can specify your maximum edge size, your minimal edge size, the ratio between two edges, and your curvature refinement, and just use this simple API to optimize your mesh. Also, you have access to distancing of domains. So the calculation of a signed distance function. This is the implementation of Charles-Laponian Pascal frame. So usually you specify an interior element attributes, you build your finite element space, and then you just specify that you want to distance the mesh. So here is the interior label. Here is the signed distance function associated with this domain. Of course, you typically want to advect this level set function by so the resolution of this advection-like equation. And Rodin just does it by calling advect on the distance function, and you give a displacement, and you give a nice time step. So all of the previous tools are commonplace in shape optimization algorithms. This is nothing new. It just makes it easy for you. So I've been quite fast until now. So because I want to really present the application of Rodin in a real shape optimization example. So a quick refresher: what does it mean for a domain to be shape differentiable? So you can naturally define the derivative of a domain, or with respect to a domain or the geometry, by considering a smooth vector field and displacing all the nodes or all the points in the domain by this vector field. Then the deformed domain, we just call it omega theta. And this naturally induces a notion of shape differentiability. The definition is quite mathematical. The main point here is to notice that this is a type of sensitivity, geometrical sensitivity. So you can think of it as you get a quantifiable measure of stretching or compressing the domain. Yeah. So let's go on to the benchmark cantilever test case. So we consider the minimization of the compliance. So you can think of it as the energy dissipated inside the structure. And we also minimize the amount of material used, because we don't want to use so much material because it usually costs too much. You can think of the compliance as kind of the stress inside the structure. Here, we will consider omega, our shape omega, to be a subset of a hold-all domain D. So our shape omega will be, I don't know, in a box or something. And we consider L a volume penalization parameter. So the higher the L, the more we penalize the volume, and the lower volume, or the least amount of material that will be used. And we consider U solution to this partial differential equation, which is, of course, just the linear elasticity partial differential equation. We can see here the hold-all domain D, the shape omega, which is yet to be determined. We have a nice Dirichlet condition here. So to specify that the shape will be fixed at this wall, for example, and we have some pull-down force on gamma n. So we here can recognize the stress tensor and the strain tensor. We have lambda and mu, the Lamé parameters, and the n is just a normal vector to the boundary. So all classical stuff. And the important theorem here is that we can calculate the shape derivative of this system, of this objective functional, and it goes by this expression. So the actual expression is not that important here. I won't go into that. But it just means that when this value is positive, so when this integral evaluates to a positive value, it leads to an increase in the shape functional, in the objective functional. And when it is negative, it leads to a decrease. So we will typically want to infer some kind of descent direction, which gives us a decrease in the objective functional. So how do you actually represent a shape in a computer? So what we do here, or what I have done until now, is it's also quite classical at this point. You track the domain by a level set function. So here's a domain that's shaped like Mario. You usually assume that the negative subdomain of the level set function will correspond to omega. The zero level set is just the boundary of omega. And the positive subdomain is the complement of omega. So this is against D. Again, D is the whole all domain, which contains our shape. And motion of omega is performed by the advection, by just the resolution of the advection-like equation. So you advect this level set function, your inferred gradient, or the previous vector field that you have computed or somehow extracted from this expression. And this is how you usually stretch or compress a domain numerically. So with this in place, we have all the necessary ingredients to propose a gradient descent algorithm. So so the first, usually you iterate over this. So usually the first step is you find a solution to the elasticity. So you find the displacement, so you solve the state equation. You somehow compute a shape gradient from this expression. So you infer a descent direction from this expression. And you compute the sign distance function, which is our level set function. Here, the gradient descent step just takes the form of the advection of the sign distance function with the shape gradient we just inferred from the shape differential. Finally, you can just recover the implicit domain by just taking the negative subdomain of the level set function. Okay, so it's been quite theoretical now, quite abstract. There's no implementation stuff, right? I have not talked about how you can use Rodin to implement this algorithm. So this is what I will do now. So a typical Rodin program just looks like this. You include the necessary modules, so the mesh module, the solver module, the variational module, MMG, and you just gain access to the namespaces defined by Rodin. You define some parameters. So for example, you define the attributes, the element attribute of omega, which I call the interior, the complement attribute, which will be the exterior. You define some boundary attributes. You define your Lamé coefficients that you will use in the resolution of the state equation, and you define some optimization parameters. It's just the actual values are not important. It's just rules of thumb that I have chosen for this presentation. Now we give the general structure. So you define your main function, you load your hold all domain D, you define your solver, ONFPAC, you define your pull force, and then you will typically want to enter into a shape optimization loop. So first, how do you compute the displacement field U? Well, usually just derive the weak formulation associated with the linear elasticity equation. This is quite standard. And then you just expand out the terms. So we're just going to expand out the terms to implement it in code. So the main thing to take away from here is that you can, like we did with the Poisson case, we can just write it in syntactic manner. We can just take the integral of the dots of U times lambda times mu times the symmetrized Jacobian, or just the Jacobian times plus its transpose, and take the matrix dot product with the Jacobian of V plus the Jacobian of the transpose. So just this mathematical expression, you just copy and paste it here, basically in code. And then you move this guy over to this side. So just to express the boundary integral of the multiplication of V over gamma n. So also in very syntactic, very expressive code. And then you add your direct condition code. Next, we have talked about how you can infer some kind of regularized shape gradient. We need this to perform the gradient descent step, so the advection step. So usually this is a bit involved. What you do is you take the change of inner product on your working space. So you take some Hilbert space, and now you have a notion of gradient. So you are able to infer a shape gradient in the Hilbert space, so in how you do regularity, and you can compute the center direction from this shape differential. So you just solve this weak formulation again. It's just a weak formulation that we have to solve again. How do you do this in Rodin? Again, you just build the extended finite element space over the whole domain D. You write your expressions in quite a syntactic manner. So you write the stress tensor, the strain tensor, and the normal. Then you define your trial functions on the extended finite element space. Do your test function also on the finite element space. So just like here, it's just, we use the same notation. And then you define your problem. I have called it Hilbert. You write the integral of alpha, Jacobian, theta, Jacobian W. The point is that it's very close to the mathematical notation. Also for this quite ugly term, you have boundary integral of the dot product, the tensorial dot product of AE and E minus L. Here it is the expression, times the dot product of N times the dot product of the normal with W. So I think there's a mistake here, but I will clarify this. And you just impose your Dirichlet boundary condition. Finally, you just want to distance the domain, advect the distance function, and recover the implicit domain. So how do you do this? You just distance, again, just call the distancer utility, and you distance D. You advect the distance function by the shape gradient we just computed. We pass some small time step, I don't know, 0.001 seems to work. And we recover the implicit domain by the implicit domain measure function of FMG. So here we just set the boundary reference. We just want to say that the boundary reference of our shape will still be gamma. So with this, we have our algorithm and our implementation, and I will just quickly pass on to the results if I have time. So this is the problem we just solved. This is the optimization process of a cantilever in 2D. So there's quite a bit of topological changes, and it's always exact. The representation is always exact, and you can always solve the elasticity equation over this domain. Okay, so we can do this. We can do the same in 3D. We can just extend the algorithm to 3D and just consider a pull-down force here. So this is the front view of the optimization process. So it also takes the form of a cantilever, but this time in 3D. We have the back view of the optimization process. So this is the Dirichlet region. It's fixed here, and the algorithm is what happens if we have a fixed here, and the algorithm rotational force here, and we still have it fixed in the Dirichlet region. So maybe to a wall. It takes attributed a physical interpretation to this jet, but it seems to be some sort of cylinder with some legs, and I think it's better appreciated from the back point of view, where it considers that 4 legs are the best configuration. So I think I'm running low on time. So to conclude, I would just like to say that all examples can be found here at this link. They're all open source. They're all there. I usually upload many examples to make sure that everything works. And I will leave you also with some similar software which supports the automated assembly from syntactic expressions. So the difference with these softwares is that they're not oriented towards a shape optimization philosophy. So they don't have as many tools to perform this geometrical shape optimization and this thing with the implicit domain meshing and the tracking of the level set methods. So of course there's RealF, MFEM++, Phoenix, and Field++. It's not a comprehensive list by any means, So sorry if your library is not here, but yeah, this is what I want to end on. Okay.
Great. Thank you very much, Carlos, for the really interesting talk.
Sure. And if you have any questions, please don't hesitate. Maybe I went a bit too fast, but there's a bit of content to be explained. So
Yeah, I think we can take one really quick question from the audience, if there is one. There definitely should be questions because there was a lot of really interesting stuff. Yeah. Go ahead.
Yeah, so we had one there. We were wondering, are you remeshing at every iteration?
yes, I am. So
yeah, it looked like it.
thank you for
sure.
thank you for your question. Yeah, I remesh, or I generate the implicit domain mesh of the level set function, and yes, there is an mesh optimization process that is carried out. However, the mesh is known beforehand, so there's there's only splitting involved.
And the distance function, what happens when you call that? Is it when you compute the distance function?
The distance function is the level set function. I use this to represent the domain implicitly and track all the morphological changes. So the main advantage of this point is that it accounts, or can account for these holes, or merging of holes, for example, versus just mesh displacement. So if you were just displacing the mesh, you will soon get a broken mesh where you cannot do some conforming finite element resolution.